All right. Hello. Check one, check two. I think we are live. We are recording. Hello, I am Alexander Booth. I am the head facilitation instructor or the head tutor instructor for the IBM Data Science Bootcamp. This is April, May 2026 cohort, and this is your week four review, lecture review, and week five preview with our week five lecture coming up this upcoming Monday. All right, so let's start with our kind of week four lecture recap. Talked about what we went over, things like that. And I always wish I could make the forums wider, but you never can. So it is just what it is. First of all, thanks everybody for joining the live session on Monday. Great topics, great conversations around introduction to SQL. If you missed it, you can catch the recording here at our official Zoom link for the bootcamp, or as always, I back up every single video on our YouTube channel. Yeah, so this week in week four, we moved into one of the most important tools in data science, which is SQL and relational databases. This whole module is understanding about how data is stored, organized, queried, and how it eventually connects back into things we've already talked about: ETL pipelines, data analytics, machine learning, all of that good work. During the lecture, we touched on kind of the history of relational databases, which I'll get to in a sec here, how they provide that single source of ground truth for enterprise organizations, and how structured query languages like SQL allow us to pull useful information very quickly from those databases. So yeah, in the lecture specifically, here are just some of the big hits that we talked about, and then I'll go into some of the concepts that you should know. We covered relational databases and database management systems. We covered SQL as just a regular language and what it can do, querying language. We talked about OLTP versus OLAP. This is your transactional processing versus your analytical processing systems. We touched on breakdowns of entity relationship diagrams and table relationships, including primary and foreign keys. And we also discussed why we need to split tables out into those normalized forms to begin with. Then we hit on kind of your favorite acronyms in SQL: CRUD operations, your create, read, update, delete, your DDL and DML, data definition and data manipulation syntax. We talked about kind of the main clauses in the query: select, where, group by, order by, limit, joins. I would also throw having in there too. Specifically with joins, we touched on the major joins: left, right, inner, outer, and when you would use all of those. Finally, we finished up with subqueries and kind of more advanced table expressions and aggregations. And then we all brought it back into Python. We created our database from CSVs by writing to SQL, so that part of the data pipeline. Then we queried back from the database and brought those queries back into pandas for visualization and pattern recognition analytics. So big takeaways from week four: most real world data does not live in clean, flat files. It actually lives in databases that operate as your single source of truth. SQL is the querying language that allows you to access, filter, join, and analyze that data before bringing it into Python for deeper analysis. I got some few helpful links here, as well as some extra credit exercises in Kaggle. And yeah, don't feel like you need to memorize syntax, even with SQL being so ubiquitous as it is. The idea here is, so I would take it to the next level, not just understand SQL, but understand the broader architecture and systems design behind the different types of databases we discussed, as well as table relations, and then how querying just fits into the larger data science framework that we've touched on since week one. Let me do a few other recap things here, and then we'll dive into some of the other comments and content from week four. So first, we definitely talked about why relational databases and what is a relational database and why does it exist. And this, I posted one of the good articles from IBM on this, and they brought up another great acronym, which is ACID. This is one of the big ideas with databases. We want to make sure that all of our data stores are ACID compliance or ACID compliant. This allows us to have trust in how the data is being stored. So let's tie all four of these back to this idea of that single source of truth. First, Atomicity, basically everything that manipulates the data all happens sequentially as single operations. Everything happens or nothing happens, right? We all kind of do it all at once, right? We don't have partial changes, right, to our data sets. That establishes trust because when we do alter the database, we are understood that everything that we asked it to do will all happen or it all won't. C stands for consistency. Data remains in a consistent state, which again, reinforces that idea of data integrity. Isolation, the immediate state of a current query or a current transaction is not visible to other transactions. Basically, everything runs sequentially serialized operations. And finally, things are durable. After a query or a transaction gets executed, those changes are persisted, right? Even if systems fail, things stay as they were, right, or as they are. So basically, if your database is ACID compliant, it is going to have that single source of truth integrity that we need from our data stores. Cool. Let's see. We touched on, yeah, I love the brief history of relational databases. I actually did this from memory when I did it. I probably should have read up on some of the knowledges here. So some things to know about the brief history of databases that they are very old. I think they started back in the 70s and 80s. Again, I got some of the breakdown for IBM here. But your first databases existed from Oracle, from Microsoft in the 70s and 80s, and that provided a single source of truth for those enterprises running on-prem systems. Then we have open source versions of these databases, your Postgres's, your MySQLs of the world that came out of the 90s, and in my opinion, helped foster kind of the dot-com boom that took off in the 2000s. No longer did you have to buy licenses from expensive corporations just to run a website with transactions that you wanted to record. Then in the middle of the dot-com boom and the advent of the internet explosion, we had the idea of NoSQL databases, non-relational databases, which we'll touch on here in a second. That was going to be by your 2000s. And then in 2010s, of course, that's the era of the cloud. Now we're moving a lot of these database systems out of just single servers and onto cloud platforms, which also allows us to horizontally scale out our systems. This allows us to have the advent of data warehouses, such as your Redshift, Snowflake, and BigQueries of the world all came out in the late 2010s. Finally, in the 2020s, we're talking about lakehouses as your main data mart, combining the benefits of unstructured storage in your data lake with your structured integrity of your data warehouse. How do we get the best of both worlds? And all the major cloud providers and other organizations like Databricks fully support that lakehouse architecture. But yeah, to bring it back to other types of databases you may run into in the world, essentially relational databases are great for tabular data sets. Non-relational databases allow you to have data stored with integrity, even if it doesn't have a strict schema. So common use cases for this include dictionaries, so having key value pairs like JSON, storing that just as it is. Um, this can also be like document stores, which also stores things in that unstructured schemas. Popular document stores and key value stores include Redis, Memcache, Mongo. We talked about all of those during the actual lecture. And then finally, kind of your graph databases like Neo4j. We talked about that as well. We talked about Hadoop a little bit. We'll touch on Hadoop a little bit more down in a few weeks when we actually dive into kind of cloud operations, both cloud databases and cloud data science. Uh, cool, cool, cool. Let's see. We got some more acronyms going on here with cap theory. Again, big idea is like when you have one source of truth with many computers accessing it, we need to make sure that we have high availability. Basically, it's always like you always get two out of three, right? It's like you want to have consistency, availability, and partition tolerance. So you get like some benefits by going NoSQL, which allows you to have like higher availability and partition tolerance, but less consistency since it's an unstructured schema. And then for SQL databases, you have more consistency and partition tolerance, but a little bit less availability. But yeah, either way, they're all good. All right, let's see here. We talked about being that reduce redundancy, ease of backup, and database storage. A lot of good stuff in why to use relational database systems. We'll just do one or two more here before we kind of dive into week five. Yeah, let me dive into. You can read up about OLTP and OLAP on your own time. I want to touch on normal forms. So this is we talked about databases, relational database systems. The key word there is relational, relationship. So why do we need to have relationships in our database, especially for tabular data sets, right? So this is kind of the idea here is that as we start normalizing our data where we apply these set of progressive rules, a relational schema just kind of emerges from this, right? And each normal form, as you'll see, is stricter than most. Again, most databases go up to three normal form, but some go up and beyond that. And the main idea here is it's reducing data duplication, reducing redundancy, and enforcing memory optimization in the database. So let's start with the first one. First, we need to eliminate all duplicate records. We need all rows and columns to be unique. The second normal form is yeah, basically everything needs to be in its own row and column here, right? Um, yeah, pretty straightforward. It's only when we get into the second and third normal forms that things get kind of weird. The second normal form basically means that we need to make sure that we start breaking out our relationships, right? We have a student and a course, right? We have a one-to-one or a one-to-many type of relationship. We define those in the second normal form. And then in the third normal form, that's where we can add in our junction tables and everything else as well. And again, most ideas here is to have a separate like lookup table where let's say we do have like a database for schools, right? I was hoping that would have like an example here. I'll actually find like a normal form example. If I can find a good one. I want to see the first, second, and third normal form tables. Blah blah blah. You only really need to know the like the one to three here. Basically, make sure everything's flat and non and unique. Make sure you have your primary keys defined, and then make sure your foreign keys are defined. Like it's basically just like that. Dot, dot, dot. I want to see like an example table. Yes, here we go. So this is a violation of the first normal form because we have multiple objects in my purchase product column, right? This isn't a flat table. We need to have flat tables, one row, one object per row column. So that's what it's mad about here. And so we end up with this beautiful table where our product has been exploded out into multiple rows. Okay, let's go into second normal form. So this is a second normal form, and we need to fix this out. There's no need to have both the customer ID and a customer name in this table, right? The customer name is only dependent on the customer, not the order. So again, we're also trying to reduce our string duplications, right? So like John and Jane and Alice, having a text always takes up more memory than having a number. So by replacing the names kind of with the IDs, we end up being more memory efficient. We're only storing the strings once, we're not duplicating the string dependency. So it's memory efficient as well as, I guess, primary key efficient as well, right? We only want columns that relate back to the main primary key here, which is order ID. Customer name can be foreign keyed back if we wanted to do a join on those tables. So that's our second normal form here. We've removed customer name, added in customer ID. And again, here's basically a third example of that. Supplier, this is going to be repeated, more efficient to store it as a number, as an ID. Add in that second foreign key dependency. We're just going to have this crazy table of the order, the customer, and the product ID. And then we can normalize things out by what is the product name and what's the supplier, and then what's the supplier name. Basically, you can just think of it as like reducing the memory dependencies of all your strings as much as possible. Turn it into as many IDs as you can. And when you start doing that and thinking about that as your root process, I want to normalize my data out to reduce string redundancies. Then you just end up with multiple tables that are all joined to each other off of numeric IDs. That's just kind of the natural evolution of the schema from that. So that's why we end up having these relationships defined. It's memory efficient, which is great, especially for on-prem storage, and you have strict requirements and controls for how data is inserted and how it connects back to other data sets on the table. Cool. We'll kind of wrap up week 4 here by kind of touching on a couple quick things in the forums. So first, Karen had some good discussion points around procedural versus declarative language. Basically, with Python, we have to write our code that is running procedurally. It runs line by line, and we do all of that. SQL is much more declarative. We tell it what we want, we declare what we want, and then SQL ends up running the code as is and optimizes it in what we call a query plan. It turns your query into a query plan, executes it behind the scenes. With Python, the query plan is whatever code you write, right? It just runs the line by line of your code. So that's the difference between procedural versus declarative. One last note for week 4, then I'll put over to week 5 because I know we're running a little bit tight on time here tonight. I wanted to touch on, again, this is a good discussion on the benefits and limitations of relational databases, about like when NoSQL would happen. But I really liked some of Karen's posts here as well. Again, it goes back to what I was talking about normalization of tables. Again, big idea, reduce redundancy, improve data integrity. That's all the idea of having a single source of truth as a SQL database. So again, we kind of, when we do have all those normal forms splayed out, we end up with a entity relationship diagram, or ERD, that looks a lot like this, where we can see how all the foreign keys relate back to a centralized table. We already discussed ACID in the scope of this recap, so definitely look at that. And again, note also that some databases don't require those normalizations. That's your non-SQL, your NoSQL databases, such as document, key value, and graph. So if we do have semi-structured or rapidly changing and evolving data with evolving data dependencies, a NoSQL database may be best suited there. So that's all your big ideas about week 4. Crash course on introduction to SQL, as well as database and database systems. I guess one last thing before we go into week 5, I'll just touch on the code that we did together for the live session for week 4. Essentially, again, like I said, we grabbed some CSV data, read it into our data frame, and then wrote that data out to database tables. And then we ended up writing different queries within our Jupyter notebooks to practice our syntax, as well as different clauses, your order by, where, limits. We have joins, your regular expressions, string filtering, all that good stuff as well. And I think down here near the end, yep, here we go. We wrote similar queries, executed them, and then this also includes a subquery, or no, it doesn't, but it includes an aggregation, and then reading that query back into a pandas data frame where we can immediately start using it for analytics and visualization purposes. So again, good class, good lecture. Thanks everybody for joining. Good conversations, both around database system design as well as system queries. All right, let's pivot into our week 5 preview here. Still want to try and keep this relatively quick. So in our week 5 preview, here is our little bit of pandas. This is our deep dive into what we call exploratory data analysis, EDA, including deep dive into pandas, as well as introduction to predictive analytics, as we'll be creating pretty basic regression analyses and interpreting those models with various metrics and visualizations. And that's all going to be the same framework that we're then going to extend when we talk about advanced machine learning methods like random forests and XGBoost models. All right, so here's my week 5 preview here, posted this a couple days ago. Let's see. Big idea here is we're going to be moving from just working with data to exploring that data and building out predictive models. So we're going to be loading in data sets using pandas. And again, this could be from a raw data source like an API website or from a single source of truth such as SQL. Once we have read in that data that we want to analyze, we're going to walk through cleaning and preparing that data that we kind of already did as well in weeks 2 and 3. We're going to talk about exploratory data analysis, looking at different correlations, creating summary statistics and summary visualizations or statistical visualizations. And then we're going to practice building regression models, specifically linear, multiple, and polynomial regression models, evaluating their performance using mean squared error and R squared, and then getting a framework for where we're going to be going with machine learning, with train test, split, cross validation, and more advanced regression principles. So by the end of the module, we'll be building a full end-to-end data analytics pipeline in Python, which is pretty fun. Let's see. In the media set for the module 510, for media 510, it wants you to like save screenshots and stuff. You don't have to do any of that. This is like a normal week. The only grades you get in week 5 is from the quiz at the end. I do always, though, recommend saving your own backup of your notebooks and work as you go here, as it's always great to back them up, add them to your own public portfolio, as well as reference them for the quiz. All right, so let's get a quick look into some of my materials here. I've already run all the notebooks, backed them all up to my GitHub. So in my GitHub, you'll see our my overview, as well as I've already added my lecture notes for the presentation on Monday. But yeah, big idea here is we're going to be using NumPy, Matplotlib, Seaborn, Scikit-learn, Pandas, all of our favorite libraries to go from raw data to modeling that can predict a continuous target. I think in our case here, we're going to be predicting house prices at the end. So we're going to be exploring the full pipeline of data wrangling, EDA, and model development and model evaluation. So why is EDA good? Like, right, we always need to kind of get to how do I use this data to make better decisions? And that obviously comes from analyzing and modeling on the data. So we're going to start with data acquisition, right? We're going to be reading data into pandas. We're going to be messing around with a used car data set. We'll be loading that all in, doing a pandas deep dive from various data sources as well. Deep dive in pandas in terms of pre-processing. How do we impute data? How do we standardize units? How do we standardize column names? How do we normalize our data? How do we use this is different than normalizing in databases. This is normalizing our numeric data so that they're all centered on the same number. So your z-scores, your standard scalars, all that good stuff. How do we do some feature engineering? How do we create new features from categories or go vice versa? How do we group numeric data into categories? And then how do we do exploratory data analysis on that data? How do we do our descriptive statistics? How do we look for correlation analysis? And then how do we tie that into model development? Now that we know that our data correlates or has some pattern signal with a target, how do we start fitting multiple models and regressors? How do we evaluate the goodness of fit of those different models? And how do we visualize the goodness of fit of those models as well? Some of the more advanced topics of the week include model evaluation and refinement. Don't worry about this too much. We're going to dive a lot deeper into these advanced modeling topics in weeks 7 and 8 coming up here in a couple of weeks. So it should be a fun couple weeks here. Key takeaways from the week, in my opinion, you should definitely have a stronger sense of data acquisition and data types and data wrangling. So again, 80% of a data scientist, data analyst job is cleaning data. So having a lot more practice with that this week. Big ideas are mostly on EDA as well. You'll see in the lecture on Monday, I'm going to dive deep into creating those visualizations and statistical plots with Seaborn and Matplotlib. And again, the model development work, we're going to reiterate in week 7 and 8. So don't feel like you have to understand it completely now, but you should understand the framework. You don't know what you don't know. So you should understand how do we go from data to looking for signal against a target to then building a baseline model, typically a simple linear regression or polynomial regression. And then how do we evaluate how well these models work in terms of various metrics, such as MSE and R squared, which are regression metrics here. So pretty fun week. And again, if you want to look at my lecture notes, which I usually don't have when I do this, I got them as well. So you got my lecture notes right here. Let's see why data analysis matters, understanding data, wrangling data, blah blah blah, EDA, visualization, group by, model development, various regression models, and model evaluations. And I think that gets us to the final end here. I won't preview the last notebook because we'll do that live on Monday. But hopefully this is a good introduction to week five here. Week five to me is a very fun week. It's got a decent amount of notebooks, but it's still a lot of fun. And of course, where we're going from this next, week six is going to be a deep dive into visualizations. So not only visualizations, but data applications and interactive dashboard design. We do all of that on week six. We'll be culminating in creating Dash applications using Plotly for those interactive dashboards. And then we get into machine learning, week seven and eight, and then capstone and advanced topics, week nine, and closing out week 10. So home stretch here. You are all doing fantastic. I'll make sure to get this recap video posted up into the forums by the end of the weekend, and I'll see everybody for our next live session, which is the week five live session on Monday. Please reach out on the forums if you have any questions, and I'll see everybody in the next live lecture or online on the interwebs. If you're following these on YouTube, then hello to the YouTube audience as well. So we'll see you in the next live session as well. All right. Thanks, everybody. Have a great night. Have a great rest of your weekend, and I'll see everybody in a couple of days. Take care. Bye.